Hey everyone. Yeah, I'm rocking my Daytona shirt because I can't rock my company's shirt yet because we're in stealth. Let's see. All right, so there have been a lot of really cool things that have been spoken about tonight. I want to talk about something called automatic prompt optimization. I think it's a really cool and powerful technique. I'm using it at my company. I don't see a lot of other people using it, and I think it'd be something that everyone here would probably benefit from. So, just a quick introduction for me. My name is Sherwood. I'm the founder and CEO of this mysterious stealth startup, which we will be coming out of stealth here in a couple of weeks, so I'm excited to share that. Currently focused on agents, obviously, developer tools, infrastructure, DevOps, observability, related topics. In the past, I was a tech lead at a company called 11x, which is an AI sales tech company. We built an AI SDR. And then I was also a founding engineer or infrastructure engineer at Brex, and also founder and CEO of a YC-backed voice AI startup. Who here is building an AI agent? Basically everyone. Do you wish your agent was smarter? I know that I do. We have a really smart one, but do other people feel the same? Yeah. I wish my agent was like Claude Code level smart, like Opus 4.5 level smart. The only question is, how do we do that? Let's talk about sort of traditional methods of making your agent smarter. So there's pre-training, there's supervised fine-tuning, there's reinforcement learning and all of the other variants. We've got RLHF, RLVR. And the one thing that all of these techniques have in common is that they involve updating model weights. This is also referred to as gradient descent. This might be basic for some people, but gradient descent is basically a fancy way of saying we're gradually, iteratively taking these tiny steps towards the minimum value, which is the best value in something called a loss function. And when you do gradient descent in 2 dimensions, it looks like this. When you do it in 3 dimensions, it looks like this. And if there are more dimensions, it looks like this. Problems with these traditional methods. Well, first of all, it needs a lot of raw data for pre-training in particular. For pre-training, we also require a lot of GPUs. For supervised fine-tuning and reinforcement learning, we need a lot of examples. All of these things can take a long time, like a pre-training run can take many hours, days, weeks. You probably need a PhD in machine learning. And a lot of the tooling's in Python. I hate Python personally. So I will say just no thanks to all of that. But what if I told you guys that there's another way of making your agent smarter that doesn't involve any of those problems? It's really easy and it's pretty cheap. You're already kind of doing it, and that is prompt engineering. Now, personally, I think prompt engineering kind of stinks, and I don't enjoy it. It takes forever to do. There's tons of trial and error involved. It's a very slow and painful development cycle. You're not guaranteed any results. This is probably the most annoying thing about prompt engineering, right? Like you do it for hours at a time, and then you just don't know if it's better or not. And then every time a new model release happens, you've got to rewrite all of your prompts and repeat this process. But there is a way that we can use AI to make this process better. And that is called automatic prompt optimization. So automatic prompt optimization in a nutshell, it's basically when your AI writes your prompts for you. And optimization is performed against a set of pre-existing evals. So the bad news about this approach is that you got to have some evals, and that's a controversial topic. But this is a pretty new and it's a powerful way to improve your agents and make them smarter. Now I'm going to talk about something called GEPA. And GEPA is like an instantiation of automatic prompt optimization. This is just one example of how to do that. There are many different algorithms and techniques for automatic prompt optimization. GEPA is one of the more popular ones. So this is pretty new. It was created by Berkeley researchers in July of last year. The name comes from the combination of 2 words, which are genetic and Pareto. Both, it's very academic sounding, so I'm a TypeScript developer. We don't do academia. Genetics, this refers to the fact that the prompt is optimized through this evolutionary process, as you'll see in a minute. And Pareto refers to the fact that the prompt is actually optimized, like in a mathematical sense. And it's hard to explain, but like it's actually the optimal prompt. Some terms you should know about GEPA before we get into an example of how it actually works. First, the candidate. The candidate is basically a version of your system prompt that may or may not include some minor tweaks, which are called mutations. Then there's the pool. The pool is the set of candidates that are being considered at any given time. Then there's the generation. Generation refers to one loop of this optimization process. So that process consists of 4 steps. There's the evaluation, then there's the reflection, then there's mutation, and then there's selection. So evaluation is obviously when you run your evals. Second one, what's the second one, everyone? Pop quiz? Reflection? Great. So reflection is when you reflect on how those evals went. Then mutation is when you generate new mutations based on those reflections. So you're kind of saying, this eval case performed badly for this reason, and I think that if we made this minor change to the prompt, it could perform better. And then selection is when you select the specific candidates that will be included in the pool. So we already talked about reflection. Reflector is the actual LLM that does that reflection, and the mutator is the LLM that generates mutations and then applies them to create new prompts, i.e. new candidates. So let's quickly fly through a GEPA run. There's going to only be 2 generations in this run. In the first generation, we're starting with a single candidate. This is your seed prompt. It could be like hello world. If you want to do a really long GEPA run, you could start with an empty string. And then for each of the candidates in our pool, we only have one, we're going to run our evals, reflect on those cases, generate some mutations, apply those mutations to create new system prompts, new candidates, and then run those evals against each new candidate. Then we will compare all of the candidate scores and determine something called the Pareto frontier, the Pareto candidates. And we'll talk about that in a sec. And then we add those Pareto candidates to your pool, and we're going to get rid of all of the other ones. Let's talk about generation 2. In generation 2, you have a bunch of candidates in the pool, and you just repeat that whole process. Over time, it starts to fan out. It starts to look like this, a little bit like that. It gets crazier, more magical, and eventually you have this amazing system prompt because of evolution. This is what that looks like in a less magnificent way. And I want to talk about the Pareto frontier a little bit. So Pareto is kind of a fancy word. This is the way that GEPA is selecting the top candidates from each generation to include in the pool. It only includes Pareto candidates. What Pareto basically means is the optimal solution for 2 or more objectives. Some related terms to this are dominated and Pareto space. I think it's easier to just visualize it like this. And you'll see there's this red line, and that red line is what's called the Pareto frontier. These red dots represent candidates that are optimized, truly optimal. Like between objective 1 and objective 2, there's no way that you can change anything to make objective 1 better without making objective 2 worse, and vice versa. And that is compared to these blue and green dots, which are considered dominated, which is an intense term. But obviously, like this blue dot, you could improve objective 2 and also improve objective 1. So this is what the Pareto frontier means. We basically only want to keep these red candidates on each generation. Some questions you should be asking about this, if you've been or maybe if you're a little familiar or you're just super sharp. One is like, what's the difference between an objective and an evaluator? This is really hard to articulate, and I'm probably going to fumble it. But evaluator, they run on your individual cases, and they produce these measurements. And those measurements are actually inputs for the objective. And the objectives are the thing that determines Pareto space, that square. An evaluator exists independently of GEPA or prompt optimization. Next question, can the mutator propose more mutations than the pool size? Yeah, it can. You can generate a ton of different mutations. The pool just determines the number of candidates that get transitioned from one generation to the next. So you might generate lots of mutations, maybe like 100 of them, run evals against all of those, and then maybe only like 10 or 20 get included in the pool. What happens if there are more candidates than the pool size? There's some tiebreaker logic. And there are different types of tiebreaker logic that you can use in GEPA. Even randomization is like one valid tiebreaker approach. There's another approach that involves keeping candidates that are sufficiently different. It'd be like keeping the top red candidate and the bottom red candidate, the ones that are furthest away, because you don't want to sort of cluster all of your candidates in one place. If there are multiple candidates on the Pareto frontier after the last generation, the final generation, like let's say you've got like 5 Pareto candidates after your final generation, you're like, which one of these system prompts do I use? In that case, it's actually up to you to decide. All of those candidates are considered optimal, just in different ways. And optimization and that decision are actually 2 different things. Does the reflector consider the entire agent trajectory or just the final response? It considers the entire agent trajectory. So if you're doing GEPA right, then you are looking at everything that happened up from the start of the agent running that eval up to the final response. And you can actually steer your agents to avoid kind of like bad pathways to a good solution using this technique. I won't spend too much time on this because I don't have a ton of time left, but I will talk a little bit about our custom GEPA implementation. There are GEPA implementations you can use off the shelf. Spoiler, they're all in Python. And one of them is, I guess the sort of the canonical one is implemented as part of DSPy, which means it's really coupled to DSPy's, the DSPy framework and some of their concepts. And so that didn't suit me as a TypeScript developer, so I went and built my own. It consists of basically a CLI tool. It works with all of my company's existing eval data sets, so we're sort of piggybacking off our pre-existing eval tool. It supports checkpointing and restarting from checkpoints. This is kind of interesting. When we first built this GEPA tool, it was quite slow because you're running a ton of evals, and if you don't have like great parallelization or you don't have a machine that can parallelize them well, then these runs can take a really long time. Like we had a run that took 2 days. We've now increased our parallelization, which makes them much, much faster, but we had issues where sometimes those long runs would break halfway through the run, like there's a timeout or some exception, and we wanted to be able to restart those runs midway through, so we established a checkpointing system. Basically, we're writing the state of the run to a file at different points. And then you can restart from those checkpoints, which is great. The run state, it gets saved to S3, so you can also pull those down from S3, which is nice. And like I mentioned, now you can run all of those eval cases in parallel, so I think that 2-day run is now like 2 hours. Here's what that looks like. I don't know how well everyone can see this. This is what it looks like basically when you print the help screen for the CLI tool. And you're going to see a bunch of little options here. These are the hyperparameters for GEPA, or just the flags for our tool. You'll see things, some familiar things like the agent that we want to optimize, the data set that we want to use. You can run with a particular case, which is not something we do very often. The number of iterations or number of generations, those things are synonymous. A max size on our pool. We can have max number of mutations or candidates per generation. We can specify specific objectives that we are optimizing for. And then our reflector model, our mutator model, and some other things. It's implemented across 3 different packages in our TypeScript mono repo. We use Turbo repo, which is like game-changing, life-changing tool, so that we can do like direct imports of local packages without having to publish anything. Those 3 packages for us are this evals package, then there's the datasets package, and then there's the GEPA package. Evals is badly named. This is where the CLI tool actually exists. Datasets is where the datasets and cases and evaluators are implemented, and then GEPA implements all of the GEPA logic. Here's an example of the output. Again, probably hard to see here, but in the top half, what you're looking at is sort of some of the evals that have been running for a candidate. And then around here, you'll see a generation 3 complete, pass rate 70%, pool 5, frontier 3. In this case, our objective is the pass rate, which our current top score is 70% after 3 generations. The size of our pool is 5, and there are 3 candidates on our Pareto frontier. And then below that, you'll see it's reflecting, and then it's generating new mutations, then it's applying those mutations, and then a new generation begins. There's a selection process too. Here's what one of those state files look like. It is, these get really big because we include everything, like every test case, every output, every evaluator output. It's a lot, every generation. But this is just the top part. You can see there's a key here that says config. That shows where, that contains all of the initial parameters. Then there's the data sets we've selected, our initial seed prompt, and under generations, this is just the result of every generation that's been run thus far. Using one of these files, we can, this actually serves as both a results file and a checkpoint file, so we could restart a new run from this file. And we have a little HTML page that when you load it with one of those files, you get this really nice GUI for sort of exploring the file and all of the settings and the different cases, et cetera. Let's talk about challenges with prompt optimization in GEPA specifically, and the first one is evals. Just evals are hard. There's some tools out there for doing them, but even with the tools, there's a lot of work involved in creating these cases. There's mocking we found to be really challenging. You can mock individual tools, but if you have an agent that could call a tool n times with n different natural language inputs, then like how do you mock all of that? We're also mocking databases and API calls to external parties, so that gets really hard. Versioning is hard with evals. Obviously, if you run your eval set once and then you change the evals and you run it again, you can't compare those two results, so versioning is super important. And then just tracking and comparing results in a convenient manner. That's also a pretty hard thing about evals. So with GEPA and prompt optimization, unfortunately, you're exposed to all of the same challenges. Hyperparameters, just the settings for the GEPA optimized tool. How do you know like how big your pool should be? How do you know how many mutations should be generated per generation or how many generations to run? I don't know. We are right now just experimenting and trying with a lot of different parameters to see what happens, but figuring out how to do that is a challenge for us. Long runs, they are hard. They were particularly hard before we figured out our parallelization and before we implemented checkpointing. Versioning becomes a problem again when you consider GEPA and prompt optimization, because now you're also versioning the reflector and the mutator, right? Other things that are now affect the final result. And then cost, I put a question mark here. We are running a frankly shit ton of evals when we do this. And so it does add up. Like sometimes we have runs that are a few $100s. In terms of future work for our team on this, first is obviously just creating more data sets and cases and creating better ones, pruning them. There's also co-optimizing multiple system prompts. And what I mean here is like if you have a multi-agent system, a parent agent that calls a sub-agent, and both of those have a system prompt in it, you could optimize the parent sub-system prompt, but have a static sub-agent prompt. And you'll be at sort of a local optimum and vice versa. So what you want to do is co-optimize these two prompts together in a single GEPA run and find the best combination of those two prompts, the ones that kind of work best together. That's not something that we've implemented yet, and that will add a big dimension to the challenge for us. Improving the dashboard, hosting this dashboard somewhere. Right now it's literally an HTML file. And then starting and stopping runs from the dashboard I think would be really nice quality of life improvements. Some open questions related to GEPA and to prompt optimization. One is just what's the ceiling? Like how much better can we make agents with prompt optimization? And also does this technique work better with specific models than other models, or is it kind of consistent amount of performance gain that we can get by finding the optimal prompt across all models? Also, how does prompt optimization compared to like other ways of improving agents? Like the things that I mentioned at the beginning, like pre-training and supervised fine-tuning and reinforcement learning. Is this like on par? Does this come nowhere close? And then is prompt optimization more or less important than context engineering? For example, let's say you have a prompt that injects some information from a retrieval system. The format of that information or the amount of that information also determines the performance of the agent. Like, should we be focusing our efforts on optimizing that system prompt or on optimizing the format and shape of that data that's being retrieved? And then, are there other prompt optimization techniques that are better than GEPA? I don't really know of that many other ones, but I know that this is sort of a family of approaches. So in theory, there could be. And then if you're interested in learning more about this stuff, I highly recommend checking out the original GEPA paper from July and Matei's talk. Matei is the CTO of Databricks and one of the Berkeley researchers who put out this paper. He has a really great 10-minute talk on this subject, which is way better than mine. And I think this company Arise that does a eval tool, they have a feature called prompt learning, which is sort of another similar prompt optimization approach. It's not GEPA, but it's in a similar vein. And they've been writing about it. And I think if you're interested in learning about prompt optimization in general, I recommend checking out those posts. And it's obligatory. I'm hiring. We've got a decent-sized team, and I've already raised. So if you're interested in working on problems like this, would love to have you. Definitely reach out. Yeah, and that's everything for me.